Hello, my name is Dr. Beanut, and today I'm going to be doing a little video on special relativity. Now, I'm not going to get too much into it, to be honest. I want to save that for another video in the future where I go into more detail, but this video is mainly a video response to a video I saw by the channel Ask Us Whatever. And I'm not sure who the us is there, but I know there's a man that talks there. I don't know the bloke's name, so I'll just refer to him as whatever. Now, I want to make a response to his video on Lorentz transforms, derivation of special relativity forms. And it's not a video going against the points he made. Actually, the points he made were very accurate. And, while experimental evidence may be stacked against him, I want to give a little perspective here. So this is a video for physicists and non-physicists alike. But obviously, if you've seen this guy, it's a small channel, small video. You probably, if you've watched those videos, you might be a little more knowledgeable in this field. So this video isn't so much for anyone. I would say this video is definitely targeted more at someone who already understands the tenets of special relativity, at least to a certain degree. Although I will be making a video in the future actually going through the details. But for now, not exactly. But I do want to give a little context, just to maybe poke some fun at special relativity for those who haven't really delved into it at all. And give it a little context of what is relativity and what is special relativity. If you already know about this stuff, this will only take a minute, so just bear with me, but it's always good to give ourselves a little refresher. So the study of, maybe I should say the mathematics behind special relativity came out of late 19th century, early 20th century mathematics on light, and seeing light as a wave of electromagnetic fields. And it came out of the idea that the speed of light is the same in any reference frame. Well, what does that mean? What's a reference frame? So, real quick, let's understand what relativistic mechanics are, or just what relativity is in general. So, we refer to a subject, and a subject is the thing that me, you, anyone, anything is looking at. And sorry about that, just had a call from grandma. Can't miss one of those. Where were we? Subject, right? So subject is what we're looking at, and the idea is not everyone sees the subject in the same way. Just like with a pen here, your perspective on that is not the same as my perspective on that. I see something that looks like this, you see something that looks like that. And we can use Euclidean geometry, things like angles, to figure out how the perspective looks different. The distance you see, the distance I see. And the idea is that space-time, what makes up both space and time, is also a Euclidean geometry. So when we talk about velocities, we can talk about them in this sense of distance and scale. And I'll explain what that is and how that comes into play with the postulate of special relativity. But just to understand what reference frames are, this idea that I can view this subject through different windows, so to speak, or reference frames. So this here is the unprimed frame. We typically consider that the frame that we are looking through. There's also the primed frame, which I'll denote with a dashed line, and the idea is we denote that with a prime symbol, saying this is the frame through which another observer is viewing the subject. And the idea is, in our own frames, we see the subject with different properties. One of those is velocity. If I view the subject with some velocity v, the primed frame views the subject with some velocity v prime. Now, in the video Ask Us Whatever, there was a criticism of an assumption made during derivations of special relativity. And that the assumption that's made when one derives special relativity is not really so much of an assumption as it is stating a case. a specific case where v prime, the velocity, the subject in the primed reference frame, is equal to negative v. This is not always true. Obviously, v and v prime can be a bunch of different things, not necessarily opposites. This is just an assumption made to simplify the mathematical formalism, and the real assumption, this is actually not an assumption, this is a case. So we denote that with case, right? The assumption is that whatever the mathematics needs to be to make this case work under the postulate of special relativity is the same mathematics for any case. The idea is we use a specific case to show that the mathematics can't just be anything to work in every case. They must work in this case, so they must be something that applies to this case. And then we just use that same thing for any other of the cases. It's a simplifying term, and this is done a lot in mathematical proofs, but it does lose generality. And it's important to note that the critique on this is not so much a critique of this assumption here, but the assumption that the mathematics specialized for that case is the same for every other case. And while the evidence stacks up for that, that is, the model seems to hold true under that assumption, it does not mean that this is mathematically correct necessarily, and that this model in theory can also break down. In fact, special relativity was a model made on top of Galilean relativity, which was the idea that you just add velocities together. So if you had a boat moving and someone threw a ball on the boat, the ball's velocity from someone watching the boat moving would be the speed of the boat plus the speed of the ball from the perspective of the boat. Now that worked, and evidence supported that, given things like boats that move relatively slow, but throw in something at the speed of light or near the speed of light, it breaks down. An experiment shows that. So there's no saying that there might be some other parameter included that breaks down special relativity. And in fact, there technically is, and that is this assumption of using Euclidean geometry to begin with, which breaks down at super large scales when it comes to things like gravity, which are shown to be shown by general relativity. But that's a whole nother story for another day. This case here simply says we're looking at v prime equals negative v. That would be like if I saw v as this of that subject, then this prime frame over here sees it as the opposite of that, whatever that means. What I'm going to do is I'm going to show how actually specifying this case gives rise to something a little more intricate and is possibly overlooked during derivations of Lorentz transforms. And the way we're going to do that is starting by stating the postulate of special relativity. Now, like I said earlier, the idea of special relativity is that velocity itself is part of a Euclidean space. And this is formalized in the following terms. That is, in the unprimed frame, we can take the delta x spatial interval squared minus this c delta t interval squared. And what that is it's the speed of light, which is fixed between frames, times the time that I've measured in my frame throughout the time I've measured the delta x interval. Right? How much time have I been measuring that movement for? And this is actually can be represented as something like the distance that light travels across the same time the distance the frame travels. Now, might not make too much sense right now, but just bear with me here. The idea is we set that equal to some distance delta s squared. This is a Euclidean geometry described by Pythagorean theorem. Sure, there's a minus sign here, but you could rearrange this to get something like a right triangle and the Pythagorean theorem. This is no different than a distance equation with spatial units. The idea here is that space-time is one structure that obeys a certain Euclidean geometry described thusly. Now, the idea is that we also can do the same thing for the primed frame. For some delta x prime, a spatial interval we measure from the primed frame, minus c delta t prime, which would be the distance light travels across that same spatial interval, across the same time we measure that spatial interval squared, is equal to some delta s prime squared. Now these two things alone don't really tell us anything. It's just a way of describing the space-time in Euclidean geometry. What the postulate of special relativity states is that delta S squared is actually equal to delta S prime squared. And what that means is we can actually equate these two, such that delta x squared minus c delta t squared is equal to delta x prime squared minus c delta t prime quantity squared, regardless of the two different reference frames. So, what we're going to do is rearrange this a little bit to see how we could get something in terms of c, because c is our fixed constant here. So if we can describe things in terms of c, it might help us to reveal something between these two reference frames. So what we're going to start by doing is moving all the c terms on the same side.